Hello everyone, this is Ali with VIAS. Welcome to our webinar, and I'll soon leave the word to Tim Hunter. TrueLoad is our partner, and I hope that this presentation will be very well received and you will definitely want to learn more about TrueLoad. I just want to take a minute of your time to briefly talk about who we are. So we resell Dassault Systèmes Simulia products, and also we resell CATIA and Delmia, and Delmia is the digital manufacturing platform. And we also provide engineering consultancy, software automation, and customization services. We also teach Simulia training courses. And for consultancy, we are not tied to any software. We can use whatever our customers would like and would request. And we have multiple industry experience, so we can talk to you about your problems and look for a way to solve it using simulation. And our team consists of like engineers with PhDs and masters in solid mechanics, fluid mechanics, materials and corrosion, etc. And we are also into 3D printing and simulation of 3D printing. And that's something, that's an upcoming subject, a popular subject, and we would be happy to help you if you have any needs for that in that area. So our technical capabilities, you may see it on the screen. We do provide services for design analysis, validation, fracture mechanics, optimization, anything which is multi-physics simulations. We do crack propagation, fatigue analysis, and we also do FEA model validation testing. And if you become a software partner, a software customer of ours, we also offer some complementary benefits like free Abacus Simula trainings in class or online, or we can also review your processes free of charge, and also look for ways to develop how your simulation service is set up, and we can try to improve it. So I'll just leave the word to Tim now, and he will introduce himself, and he can share his screen to start the presentation for TrueLoad. So
okay.
Tim.
Thank you, Ollie. Thank you very much for that. As Ollie had said, VIAS is one of our great software resellers and technical partners for the Restore family of products, the main of which is TrueLoad. And we've got a nice presentation today to kind of introduce you to TrueLoad, and it's going to span a very wide variety of platforms from automotive, aerospace, and oil and gas here. So we're actually going to have an example with blowout protectors and flanges in this presentation. So we've got a lot of material to cover. I'm going to try to get through the material very quickly. The webinar platform you're on has got a Q&A capability to it. So please, if you've got questions, type in the Q&A area. We'll try to get your questions at the end. And if we can't get them to you while we're doing the webinar right now, we will definitely follow up with you and give you some, try to get your questions answered. So,
sorry, Tim, sorry to interrupt. Your voice wasn't very clear. So if maybe you can dial in using the phone.
I am dialed in using the phone. So is this better now?
Yes, better. Yes.
Yes. Okay. So I'll just make sure I speak up more clearly. Okay. I'll just kind of speak loud. Okay. Very good. So, we'll get right into the presentation. So this is a bit of a teaser slide. Okay. So this slide is showing some feedback from one of our customers from a project we did with them, and we were able to do their equivalent of $150,000 of work that would only take them 30 weeks to do. Using TrueLoad, we were able to do the same work in under $1,000 in 8 days. So this is the type of cost-benefit analysis you can get with TrueLoad. We'll get back to this at the end of the presentation. This is to whet your appetite and make you hang on to the whole thing, okay? So, a little bit about Wolfstar Technologies. Wolfstar Technologies was founded in 2010 by myself, Tim Hunter. I'm the president and the developer of the software. Prior to starting Wolfstar, I'd been at Harley-Davidson Motorcycles, and I was chief engineer of vehicle structures. And I'd been involved with every aspect of product development, from concept to design, analysis and testing, launching in production, dealing with styling and marketing and customer issues. So I've been involved in every aspect of product development. I understand what it takes to get products to market, and I'm sure we've got tools here that can help you and help you get your product to market faster and better. Since we started our company, we've got great partners in our software partners. We're Dassault Systems with Abacus, Ansys, MSC, CE-Tron. These are companies who see the value in our product and want to help us get our product to their customers so their customers can be more successful. So we've got some very, very great, strong partners here, and I think we've got a great product here that you'll be able to use. So the products from Wolfstar Technologies are these. Our main product, our flagship product, is a product called TrueLoad. So TrueLoad turns components into load transducers. And we do this by taking an FEA model and having you put unit load cases on it. And we identify the placement where the strain gauges based on those unit load cases and store correlation metrics to this. You place strain gauges on physical parts, and we'll take those measured strains times that correlation matrix and that calculates the loads. We're essentially just turning your parts into a load transducer, and we're doing that with strain gauges and your FEA model. We're just making load transducers. Our second product we've got here is called True QSE. QSE stands for quasi-static events. And this quite simply takes results from your FEA model, and we can attach user-defined functions to those results, and then linearly superimpose them all together. It's a pretty straightforward procedure. It's very flexible and very efficient, and lets you create some very complex results from very simple load cases. And that by itself is great, but what happens is that we bundle True QSE with TrueLoad, and because what's going to happen with TrueLoad is you're going to get time histories of loading that correspond to unit load cases in your FEA model, and True QSE then is essentially a post-processor for your TrueLoad results and lets you look at all the results that you've measured from the loading in the field. So this is a very nice way for you to post-process and look at your model. And then the third product we've got is a product called True LDE. And LDE stands for Linear Dynamic Event. And this is a product that is aimed solely at the Abacus market, and it basically fills a very nice opening in the Abacus market for being able to post-process star modal dynamic, star steady state, and star random response. It's a very efficient post-processor that allows you to pick any node or element on the model, generate any results you want, create optimal deflection shapes. It's a very nice, easy-to-use tool for looking at your linear dynamic results. And all of these tools then have got a nice interface to FESafe. So FESafe has been a partner with us from the very beginning. We no longer have got a formal relationship with FESafe, but FESafe from the very beginning saw the value in our products. When we met with John Draper, when we were first launching the company, he saw what we could do, and he knew that we had to have a relationship with FESafe because we're basically trying to make sure that the load histories are correct so that when you go to do fatigue analysis, you get the right results by fatigue. So that's one of the aspects of using TrueLoad and the various tools. So you don't need to use, if you have FESafe, then our tools make using FESafe much easier, but you don't need to have FESafe in order to use our tools, okay? So it's just an extra benefit, and if you've got FESafe, we'll make using FESafe better. Okay, so let's get right into the discussion on TrueLoad. So the whole motivation behind TrueLoad is quite simply, what's the load? So if you were an engineer that had to design components for this motorcycle, and you look at this loading, and it's very nonlinear, it's almost impossible to measure, and it's impossible to calculate. But you as a design engineer and as an analyst are responsible for the successful design of the components, but you don't have the loads. How can you do this? So what we recognize at Wolfstar Technologies and with TrueLoad is that we can turn each individual component into its own load transducer, because the swing arm, the crankcase, the frame, the handlebars, the fenders, the gas tank, they're all basically responding linearly. And we're going to take advantage of that, place strain gauges on those components, and let those components become their own load transducers. This is a first-to-market solution. It's based on a technology called influence coefficients. Influence coefficients have been around for 50 years or so, but influence coefficients historically has been a very laborious experimental procedure and it's prone to error. And we've taken out all of that trial and error that happened experimentally. We've eliminated that leveraging your FEA model and the power of being able to script and program and do optimization. So this is what TrueLoad's doing, is that you're turning your part into a load transducer with optimal strain gauge placement and leveraging your unit load conditions. So our product works with all of these types of products that are on the screen here. So whether the product is getting loading from the environment, getting loading from the users, getting loading from internal loads for itself, we can basically help you understand the loading on your product so you can use those loads to design and analyze and optimize your product better. So we've got customers in all these product segments, and I'll show you applications for these as well. So the product simulation workflow, we're all doing this. This is nothing new to anybody. Product simulation these days, we start off with CAD models. So we get very good CAD models, whether it's coming from ProE, CATIA, SolidWorks, or whatever. And then we take those CAD models and we'll bring them into our FEA environment. So whether you're using, Nastran, Abacus, ANSYS, any of these environments, they've got very models. You put your material models on them. They've got great solution techniques. And then the second you go to throw them into a solve, you've got to come up with some loading. So typically that'll be some loading that you've calculated on the back of a napkin using engineering calc, or maybe there's some standard loadings that your customers have, that your companies have, and you use those loadings to create FEA results, and you evaluate your product that way. And oftentimes you want to take it to the next step and do fatigue analysis with tools like FEA, where you can take these loadings and bring them into your fatigue analysis software. But in order to do fatigue analysis, you've got to define the events. So typically you'll need to make up the event to kind of show the repeats of the loads in the structure in order to understand what's going on. So, and then once you've done that once, you can always throw it into optimization tools, be it Top.ai or other optimization tools, to automate the process and do this automatically multiple times. So this is a pretty standard environment here. And when you look at this, and all the little blocks in this diagram here, there are very mature products in all of these blocks, except for the most important ones, the loading and the event definition. Those are huge missing blocks here. And if you don't get the loading and the event definition right, then you're just doomed to not have successful analysis. And what I hope to show you today is through this presentation, we're going to fill in those blocks, the loading and the event definition. Okay. And this is a little bit of a repeat of that, but a historical concern with loading now is oftentimes you go in to do an analysis, and the biggest unknown on the analysis is the loading. Okay, so the thing that you need to do is go in and you'll oftentimes guess at the load case on the product.
Tim, sorry to interrupt again. We have some issues with the voice quality. I mean, we got some messages. So is there, and you can dial in using your.
I'll call in one more time and see what we can do. Okay.
Sorry about that, because we had some messages from our viewers. That's why I interrupted. Sorry. Okay, I apologize for that. So.
Ollie, can you hear me now?
Yes, it is much better. Thank you very much.
Better. Okay. All right. Okay. Sorry for the problems there. I'm sorry for that. Okay. I'm going to get right back into it. So one of the biggest problems then with doing an FEA analysis is that you just don't understand the loading. Okay. So you'll have a great mesh, you'll have a great solver, and then you go to throw it in and you guess at the loads. So if you don't understand the loads, you're going to do extra iteration cycles. And typically what people do to try to understand the loading is they'll go in and they'll go out and buy load transducers like you see on the screen here. And load transducers are fine, but every time you use them, number one, you spend money on the load transducer, and then you've got to modify your structure to use them. You've got to cut apart your structure, you've got to insert the load transducer, and you're measuring something. It may or may not be the actual load, because now you've changed the stiffness and the mass of the structure. And so you'll measure this, and then you bring that back to the analysis person, and the person doing the analysis, well, they're working on the as designed parts, not on the as tested part. And so now they got to change your FEA model to look like a test article. So it's just not a clean way to go about understanding the load and structures. And you can't measure all the loading degrees of freedom that you need. Another approach that people try to do is they try to use strain gauges. And oftentimes you'll take your FEA model, you look at your FEA model and come up with some locations to lay strain gauges. You'll talk to your colleague, come up with a few more locations. You'll lay 20, 30 strain gauges on your structure and measure these time histories of strains. And you look at the strain data and you look at your FEA model and you just scratch your head. You just can't understand what's going on. So typically what will happen is you'll pick one or two channels of data at one or two points in time and use that. Those are the strains that you're concerned with. And you'll work for days, if not weeks, trying to come up with load cases that get those two strain areas to light up the same way that they were in the field. And then once you've done that, you do your redesign. And then the next time you get to the field, you'll find out that your part still isn't working, you've missed something, and you've got to go back and do the whole process again. I have done that in my past, and I'm sure many of you have done that as well. It's just part of doing an FEA analysis without understanding the loads. So what's wrong? Your company's investing in great analysts like yourselves. They're investing in world-class FEA software. You're doing the right stuff by testing and instrumentation, and you're investing in tools like FESafe to do fatigue. So your company is making all of the right investments, but they're not getting the right answers. What's going on? Well, you just got too many variables to manage. You got the gauge locations, you got the load cases, and you got the quantity of data. So you think about, you lay 30 strain gauges on a structure, you go to the field and you take the data. It could be a 500,000 data point long time history that you've got. At every point in time in the time history here, you've got a unique loading recipe for each point in time. So if your time history is a 500,000 data points long, well, now you've got a 500,000 unique loading recipes, and you just can't do that manually. You're left in a no-win situation. So you need some automated way to understand these complex loading time histories. So the solution, quite simply, is TrueLoad. So TrueLoad in three words is just in situ load measurement. So in situ means in location load measurement. So we're going to take your components and turn them into complex multi-channel load cells, and we're going to do that by leveraging the FEA model to work with the test data. And we can work with any FEA platform, and we've got very nice plugins for Abacus CAE and ANSYS Workbench. But if you don't have those products, we've got a very good standalone product that works great with everything. So, and at the end of the day, you get optimal placement of strain gauges. And if you're using FESafe, we've got a nice direct interface to FESafe. Okay, so let me go through how the workflow works for this, okay? So the workflow for TrueLoad goes like this. We'll start off with an FEA model like normal, but rather than coming in with one complex load case, I'm going to ask you to decompose the loads into a series of unit load cases. So it might be an X component of load, like 1 kilonewton in the X direction, 1 kilonewton in the Y direction, 1 kilonewton in the Z direction. It could be a pressure load, it could be a thermal load, it could be an inertial load. But whatever you think the unit loads are, that if you could mix them together, could you approximate the operating conditions on the product? So this is your thought process here for designing the unit loads in the structure. So you've got to define that. You're basically defining what do you want your structure to sense? What loads are important to sense? And then you go into the pretest software, and the pretest software will look at the unit load cases on the FEA model and the strain results and come up with optimal strain gauge placements. And then once we've got those strain gauge placements, you can go in and reposition and reorient the gauges. And then at the end of the day, we're going to store a correlation matrix that relates the strain response at all these gauges to all of your unit load cases on the FEA model. So when we come out of pretest, we're going to have the gauge placement, and we're going to have a correlation matrix that we store to disk. Then we go into the lab, we place the strain gauges on the physical part, measure the strains, and that could be in the lab, that could be in the proving grounds at your customers, whatever is the right operating conditions to measure the strain in. And then once that's done, we then go into the post-test software, and the post-test software takes the measured strain data times a correlation matrix from pre-test to generate the loading functions. And now we've got loading functions, and these are time histories of loads, and loads are loads are loads. We could bring those into our FEA models using manual means to bring them into the FEA model. Or what I highly recommend is you use the true QSE file that gets generated automatically. And the true QSE file is going to manage all the unit load cases and all the corresponding loading functions so that you can go in and probe and query the model anywhere in the model for any stress, strain, or displacement you want. Send it off to FE Safe for doing fatigue analysis now that you've got the strain correlated loading functions, okay? So this is the overall workflow for using TrueLoad. And when you look at this, the top 4 blocks here, are you turning your part into a load transducer? And in the bottom flow chart, are you doing design and optimization now that you understand the loading? So you might do the top 4 blocks once, and then go through the bottom loop maybe 20, 30 times as you change and update your part geometry. Okay. So I've got a player piano analogy that kind of is another way to understand this TrueLoad approach. And so bear with me on this. I think it's a good analogy here. So if we were to design a player piano, we would sit down at a piano keyboard and look at the 88 keys of the keyboard, and we press each one and listen to the sound it makes. And we'd make a mapping between the key press and the sound. And we'd store that mapping between the key press and the sound as a musical degree of freedom, and we'd store all the musical degrees of freedom for the keys on the keyboard. A normal person would call that a note, okay? And then once we've got that, then we go listen to music, and we store the acoustic pressure waves over time of that music. So we record those acoustic pressure waves, and then the whole point now is we're going to take these acoustic pressure waves and project them onto the musical degree of freedom matrix, or what a normal person would call transcribing it into sheet music. And then once you've got the sheet music, then you can create the player piano roll and go. So TrueLoad works the same way. What TrueLoad's going to do is we're going to take our component part, we're going to put a series of unit load cases on our component part. Those unit load cases then are going to create strain fields on the part. And from those strain fields then, the pretest software is going to look for places to place strain gauges in order to uniquely identify each strain field. Once we've got the strain gauge placement, we go measure the strains on the physical part. And then the whole point now is we're going to take the measured strains times that correlation matrix to generate the loading functions. And then we'll get this nice time history of loading. So the time history of loading here is basically how much each one of these unit load cases is participating in the overall response. And then once we've got that, then we can play that back and create the overall operating environment on the part. So we can recreate the full field results from just a handful of strain gauges. So this is what TrueLoad does. And those of you who are familiar with the concept of modal participation and modal decomposition, this is basically working the same way. So we're basically making load modes that we're scaling the loading participation factors here. This is essentially what TrueLoad's doing, okay? So it's got a parallel to the concept of modal participation. The mathematics are slightly different, but it's very much parallel to that. Okay, this is all based on linear systems and loads. So linear systems are where loads are proportional displacements, displacements proportional strains, strains are proportional loads. It's a linear system. I understand everything in life is nonlinear. Everything's nonlinear, okay? We've got nonlinearities due to welds, nonlinearities due to bolted joints, nonlinearities due to elastomers, due to contact. There's lots of nonlinearities in our system. But what we're going to do is we're going to turn a part into a load transducer. So what we're going to do is we're going to target nominal areas on the part where the strain response is remaining proportional. Okay, we want the strain response to remain proportional. We're going to stay away from high strain gradients, and we're going to just be out nice nominal areas on the part to lay the strain gauges. Okay, and then the loading can be as nonlinear as anything. The loading can be sinusoidal, ramp loading, impact loading. That doesn't matter. I just need the strain response to remain proportional based on the loading. So I can take this diagram and turn it into a couple of equations. The right-hand side here, well, that's just F equals Kx. So that's Hooke's law. So if your part obeys Hooke's law, then true load has got to apply, because we're leveraging the left-hand side of this triangle here, which is strain times a correlation matrix is to load. So strain times correlation matrix equals load. Well, that's just the strain corollary of Hooke's law. And what we're doing is we're calculating forces as being strains from test times a correlation matrix from FEA. So earlier on, I'd mentioned that this is based on the science of influence coefficients. So influence coefficients, this is the governing equation in the science of influence coefficients. So this is what we're leveraging in this whole approach here, okay? All right, so we're not going to get into the deep mathematics here. If you're taking my training course, we would go into this more fully. But I just wanted to show you the matrices that's going on behind the scenes here. So in this example here, I've got 3 unit load cases on my FEA model, and I'm choosing to lay 4 strain gauges. So here the columns of the strain matrix are 4 uniaxial strain gauges, and we've got 3 unit load cases. So this is what we're doing here. So we're going to have 3 sets of unique strain responses for 3 sets of unique loads. We've got a nice, well-behaved linear set of equations. So this is what true load's doing to set up the correlation matrix, which is in the middle here. Okay, so I'm going to go through the workflow with a little bit of graphics behind it, and then we'll get into some example problems. Okay. So this example here is a headlamp on a motorcycle, and the analyst is looking at this headlamp and saying, well, you know what we've got here is a case where we're getting excitation from the front suspension, from the handlebars, from the frame, from the engine vibration. The analyst looks at this and says, this is basically a base excitation problem. And so he's going to choose to model this system as being restrained to ground, and his unit load cases are going to be 10 Gs, X, Y, and Z on the structure. So he's got 3 unit load cases of G loading on the structure to approximate shaking the ground. Okay, so that was his choice in setting up the model. Then he goes in and launches the TrueLoad pretest software, and the pretest software then loads up his 3 unit load cases. He then selects a subset of the model for candidate areas for placing strain gauges. And so he's being very diligent about how he's doing this. He's picking elements in the middle of the headlamp bucket and in the middle of the legs, and he's staying away from boundary conditions, and he's staying away from where parts hook up to other parts because we've got a rigid constraint here. So we're just going to have nice nominal areas that we're going to use for possible strain gauge locations. Then he tells TrueLoad that he wants 6 strain gauges and tells TrueLoad to go find the strain gauges, and it draws up the strain gauges on the screen here. So these lines are showing the position and orientation of each gauge. And once he's happy with that, then he saves the gauge information, goes to the lab, lays strain gauges on the physical parts, and then measures the strains in test. And now the whole point now, he's going to take the measured strain data then, and then turn that measured strain data into load, and we do that in post-test. So post-test here, what we're going to do is we're going to bring in the pre-test file, which has got that C matrix in it. Then we bring in the strain data file from test, and we push this button here to generate the load. And it's really that simple. There's lots of things on this form here where we can map and drop channels, we can plot data, but really at the end of the day, it's you bring in the C matrix from pre-test, you bring in the strain data from test, and you push the button. And once you push that button, TrueLoad's going to go off and generate the loading functions. It's going to generate an HTML correlation report, and it's going to generate a QSE file. And if we wanted to, we'd actually generate data for FE Safe right away. But really what I prefer to do is we go into the QSE module, and that gets generated automatically. And you can see in QSE what happens is we've got our 3-unit load cases and the corresponding loading functions that were created from the strain data. And now that we've got the loading functions attached to each one of these unit load cases, we can probe any node or element in the model to generate XY data of displacement, stress, strain, whatever you want. We can generate operating deflection shapes, or if we wanted to dump this off to FE-safe, we could go off and do an FE-safe run as well. So this is really a really great way to understand everything going on in the part just by laying a few strain gauges. But the whole point with this now is that we're trying to get the loading so we can do redesign. You know, the whole point you'd want to try to understand the loading is to try to understand the redesign here. So the way you would go about redesign is I just have you go back to the FEA model, and you can change this FEA model however you want. You can poke holes in it, you can thicken things up, remesh the part, do whatever you want to the FEA model to do your design changes to improve the part. And then the only thing I'm going to require you to do is solve the FEA model with the exact same 3-unit load cases. So we're going to solve with the same 3-unit load cases, and then we're going to come back then to QSE. And QSE then, we're just going to, once you solve it, we're going to have QSE point to the new set of FEA results, whether that's an output database or an OP2 file, whatever you were using, have you point to your new set of FEA results, and then QSE will then use the loading functions to superimpose the results based on all that, and you get to see the effects of your design changes very, very efficiently. Okay? So that's the overall process for using TrueLoad. Going to get into just some customer examples right now and go through these as quick as we can. So this first one here is a dozer application. So this is a bulldozer from one of our customers. And what we did here in working with them on this is we put XYZ unit loads on the front of the blade. We had a load basically on the hydraulic cylinder here. And on the back of the blade, there was a mechanism we had to actuate. So we had 5-unit loads on the system. And then we put 12 strain gauges on this bulldozer. What you can see here on the top right, the green curves are the measured strain from the test here. So these are our 12 sets of strain data that we used from the test. And then what TrueLoad does is takes those measured strains times a correlation matrix to generate the loading functions. And once we've got loading functions, post-test goes in and pulls out the strains off of the FEA model and plots those up in blue. So green is measured here, blue is simulated strains. You can see how closely that's matching to everything. And they thought that was great, but what they were really concerned about were these areas of high strain here next to their welds. And so they laid gauges like this, gauge number 19 as extra points of interest. And here we got gauge number 19 plotted up in green here. And then in QSE, we probed the elements coming away from the weld and plotted that up in colors. And you can see how well those strains match to what they measured in the field. So this is just a really nice example that shows once you get the overall flexibility right on the structure, the hot spots come along for the ride. Okay? Here's an example of a crankshaft on a small engine. This customer, they had a situation where they were breaking their crankshaft in their dynamometers, and they'd been working on this problem, trying to figure out how to fix this problem for 2 years, and they couldn't figure it out. And so they talked to me about it. Working with them, we came up with X and Y loads in the crankshaft here, and they knew that there was some modal content to the flywheel, so we included a torsional mode and 2 bending modes of the flywheel as well on the system. And what you're seeing on the top right here are my green and blue strain plots. So the bottom curve here, this is my best strain gauge here. So I've got maybe 0.03% error between my green measured strain and my blue simulated strain. But even my worst strain gauge is less than 1% error. It's still excellent error here on the strain response. And so we were really happy with the strain response. When I reviewed the crankshaft loading with the engineers, they said for the speed the engine was running, the crankshaft load seemed to be right. So we took that information then, ran that into FE-safe, and FE-safe identified this location here as an area of maximum damage, which correlated exactly with where they were cracking the part in the field in their dynamometers. Okay, I've got an airplane wing example that I worked up for NIAR a couple of years ago. NIAR is the National Institute of Aviation Research. And since I didn't have an airplane wing or a wind tunnel or the strain gauges to do it, I made a coupled CFD model to show how we could use this on an airplane wing. So this model that you're seeing here, this is going to be my test part, and I'm going to lay virtual strain gauges on this and collect strain data off that. So this is my nonlinear test part. It's a coupled CFD structural analysis. So it's a highly nonlinear analysis here. And then we're going to go into true load then. And I set up a series of unit load cases on the wing as pressure loads on the wing. On the top, I had 7 pressure loads on the top. I had 7 pressure loads on the bottom. True load said place strain gauges at these locations here. They're hard to see. There's little green beam elements that are looking like strain gauges. So we had 21 strain gauges for these 14 load cases. And then we went in and we collected the strain data off this nonlinear model. So the green curves are the strain data collected off the nonlinear model. And then True load took those measured strains times a correlation matrix and used those to generate the loads. And once you had the loads, we back calculated the stresses, the strains off of the true load linear model. And we've got those plotted up in blue. And here's a cross plot. We've got measured strain versus simulated strain, and showing how nicely we correlate with that highly nonlinear simulation. And then once we've got those loading conditions, then we can go and create an operating deflection shape on the whole structure and recreate what was going on. Okay. Here's the money slide example. So I want to come back and show you this a customer example here. So this is Aaron's. They're in Brillion, Wisconsin, just a couple hours north of Milwaukee, and they're manufacturers of very high-end lawn and garden tractors and commercial lawn and garden tractors. And this situation here, they had this engine deck that sits underneath their seat on their tractor here. And this was working great for them. They had no durability issues with this, but their transmission supplier wanted them to provide additional airflow to the transmission. So they had to redesign this to provide airflow. And so they asked me if I could help them out with it. And working with the engineers there, we decided that this is basically a base excitation problem because this whole frame is going over their proving grounds and bumping up and down on the proving grounds. So we decided to hold the frame to ground and apply XYZ gravity loading on the structure here with the engine on with the lump mass in the engine on this system. So we did that, and True load said place 8 strain gauges at these locations here on the structure. So we had the 8 strain gauges identified, our 3 unit load cases, and then we went in and to their proving grounds, and this is my typical green and blue plot again, okay? So we've got the measured strains here from the proving ground, all 8 strain gauges, and then what you're seeing are the blue simulated gauges, and they're line on line, and here's the cross plot of measured strain versus simulated strain. And now that we've got that, we then can take that in and create an operating deflection shape of the baseline product. So the beauty about this example here is that Aaron's had started doing the redesign of this product using your traditional engineering load cases and loading methodology. So they had made the first design iteration before they got involved with me. And they had this product on test. So they had their first design iteration on test, and they were so proud of this, they wanted to show it to me on test, and so I could see what was going on. And we went down to their shaker test to see what was going on. And they had just failed about an hour before we got to the lab, and it had accumulated 12 hours on the shaker test. And their goal was to have 10,000 hours. And I said, perfect, give me that model, let me run the true load loads into it, and I can show you the stress and strain response in that part. And then we see that this is much higher. I'm going to show you durability plots on the next slide. And then working with the engineers there, we came up with some new design. So they came up with a different hole pattern. This first redesign, the engineer had 2 layers of sheet metal that was riveted together, and we had these holes in it. The manufacturing guys hated it, and so we had to get it down to 1 piece of sheet metal, and we worked on thicknesses and went back and forth. And so by the end of the week, we'd gone through basically 5 design iterations and had come up with a solution that worked. And you can see what happened with the durability. So here's their fatigue life curve for their material. And so when you look at this curve here, they want to be at 10,000 hours. And so you basically, we want to see yellow, green, and blue on the durability plots. And their baseline was fine. There's some red here. That's only because of the RBE I've got for the engine. And then here's their first design iteration. Okay, so this failed in their lab at 12 hours, and FE Safe was predicting a failure at 10 hours. right through these locations right here. So this is just another nice confirmation that we've got the loading exactly right. And then we were able to go in and do the durability analysis on the other redesigns. And by the end of the week, we've got a design with the airflow they need, and actually with better durability than they started off with. So this is what you can do when you understand the loading, and this is where the whole thing comes in when you understand the loads, you can really cut down on the design time. So that when we talk to them, it would normally cost them about $30,000 to prototype and build and test a design. It would take them 6 weeks to design and procure, and they'd be guessing at the loads each step of the way. So if we did 5 design iterations, that would have been $150,000 in 30 weeks. And with TrueLoad, we were able to do all this in 8 days, and if you amortize the cost of TrueLoad, it was less than $1,000. So this is just the type of results you can get. So, okay, last couple examples are on oil and gas application. So I'm going to show you a blowout preventer, and then since we're getting a little bit towards the end here, I think I'm going to just do the blowout preventer, and then we'll get right to the questions. Okay, so this is a simulated example that Vias had me work up for them about a year ago to show the application on a blowout preventer. So we came up with some unit load cases that a blowout preventer would have. And those of you who aren't familiar with oil and gas, these blowout preventers are sit on the bottom of the ocean floor, and they help us make sure that the oil doesn't get in the wrong place. So there was a huge accident a couple of years ago that I think you all recall in the Gulf, that these blowout preventers were the cause there. So we went into TrueLoad with those 2 unit load cases we put on the model. The TrueLoad software said place strain gauges at these 4 locations here. And then we can then go in and once we had that, then we generated some simulated test data. So we did a simulated testing event. So we created another FEA model that could generate some strains on this model. And we actually ended up having what I'd call the perfect strain on this. And we actually introduced noise. So we actually introduced noise on the perfect strain data to just say that, you know, even though we're dealing FEA to FEA here, we're going to add additional error in just to push the system a little bit harder. And then we brought that into TrueLoad, and then this is the usual plots we've been seeing, the green and blue plots. So we've got the green curves with the measured strain from our simulation, and then we take the measured strain times the correlation matrix to generate the loads, which you see on the right here. And once we get the loads, then we can back calculate the simulated strains in blue, and here's the cross plot down here of measured strains versus simulated strain, and then you have the operating deflection shape of the blowout protector, okay, preventer. So this is kind of how it goes, and just doing a load verification, the green curves here are the original loads that we put on the FEA model to generate the strains, and the blue curves here are the back calculated loads. And you can see that we've got some noise on there, but that's because of the noise we put on the input signals. So on one of them, we had a little bit more noise, but on the other loads, we were line on line, okay? So we had 2 different loading degrees of freedom. All right, so I don't think I'm gonna go to the flange here, Ali. I think we're gonna go straight to Q&A. So I'm gonna summarize here, and we'll get right into the Q&A then, okay?
Okay, so Tim, you can see the Q&A section, right?
Yes, I can. I can see the Q&As, and let me see. I got several of them here. Let me just see what we've got.
Yes. So you can one by one answer them.
So just I want to summarize real quick, and then we'll get into the Q&A. So just to summarize, then, you know, with TrueLoad, we've got the ability to really revolutionize your product development. We'll get you optimal strain gauge placements. You'll get unprecedented strain correlation, and what's even better is that you get strain correlated load histories. And now that your engineers will actually have strain correlated load histories, when they go to do redesign and analysis, they're actually going to make the right decisions by the product. And because the engineers are smart, they know what they're doing, but if they don't have the right loading, they can't make the right decisions. So with the proper loading, they can then make the right decisions about the product. And by making the right decisions about the product, then you end up eliminating entire iteration cycles, because now you've got to cut and try much less. And I've got lots of examples where we've been able to cut out entire iteration cycles, several iteration cycles out of people's product development areas. And one more thing is that we reduce test costs significantly, because you're no longer buying load cells, which are very expensive. All we're doing is we're buying uniaxial strain gauges, which cost $10 a piece and usually take about a half an hour to install. So the test cost of a strain gauge versus a load cell is significantly less, and it's much more straightforward to use. And we're not modifying the base product. And finally, I didn't get much of an opportunity to talk about some of the advanced features of TrueLoad. We've got the ability to use sliding loads, to create sliding loads and structures, to do hybrid loading. So sometimes you can actually measure loading directly, because you might have a hydraulic cylinder or something that you can get loads off directly. So we can measure direct measured loads with the loads calculated from TrueLoad, so you can get a complete hybrid loading scenario. And then we've just introduced a very nice capability called contact control, so we can make sure that your contact loading degrees of freedom are all operating the way you expect them to operate. So this is some really powerful stuff we've got in TrueLoad, and we really make it easy to use. Okay, so Ollie, now we're going to get right into the Q&A, and I see we've got some questions here. So let's get right into it. Let's see. I've got a question here. Do you typically use TrueLoad for individual components? Is it much more difficult to utilize for an entire structure to obtain meaningful loads, i.e. a bus or a rail car that may or may not be 100% correctly modeled in FEA? So the TrueLoad technology needs a structure to work as a contiguous system. Okay, so if it's a large welded structure, like a rail car or a bus structure or a chassis structure, we can work with that just fine. We can turn that whole chassis into a load transducer, and that does work just fine for us. Where TrueLoad can't do things is if the structure is a kinematic structure. So, for example, if you've got for example, Case CNH is a customer of ours, and they create front end loaders and backhoes. And these structures are basically kinematic linkages that are all going through. I can't do one TrueLoad analysis on the entire kinematic structure of the backhoe, but what we can do is we can take each link in that kinematic system and turn each link into its own load transducer. So if the backhoe has got 3 linkages in it, we'll set up 3 TrueLoad models with strain gauges and get all the loads in the structure with each individual link, and get the loading going on into each individual link. So that's a technology that we can do, and it works very well on those structures. But you have to think about that you're basically getting the loading on each individual contiguous parts. Okay, so that's how it's working. And so we get really meaningful loads for our companies, and we can get them very good information. And Case, for example, they just issued a paper at the Abacus conference this spring showing how they use that on one of their front end loaders. Okay, let's see. We've got some more questions here. There's a question about rosette gauges. So, person's asking, do you need to use rosette gauges with TrueLoad? So TrueLoad, by its definition, wants to work with uniaxial strain gauges. So we typically are only using uniaxial strain gauges in TrueLoad. Sometimes I need to go in and reverse engineer some of my customers' problems. So sometimes my customers will give me test data that they've already laid on the structure, and they've already used rosettes. So with TrueLoad, we can create rosettes by basically placing 2 or 3 strain gauges right next to each other and either orienting them at 0, 90 degrees or 0, 45 and 90. But we can make rosettes virtually inside of TrueLoad by making 3 strain gauges placed next to each other. And I've got some really nice techniques. Either you get them laid next to each other on the FEA model, or I've got a really nice technique where I just stack 3 membrane elements on top of each other, and then we can get 3 gauges in the same spot. So let's see. There's another question here that says, is there a maximum number of loads/gauges? So TrueLoad does not have any programmed in limitations. So there's basically, you could have an infinite number of strain gauges, an infinite number of load cases, but the limitations will be your computer processing power, your computer memory, your hard disk's capability on your computer. So just the typical hardware issues that you'd have. But really the real limitation comes in is actually your data acquisition capabilities, because you typically don't have an infinite number of channels you can collect in the field. You typically will have a data acquisition system that can take 32 channels of data or 64 channels of data. So that's usually the limitation, is actually the data acquisition equipment you have. That's typically the limitation for people. But there's no program limitations in the software. Let's see. There's a question here about multi-body dynamics. So this person is asking, how is TrueLoad different than working with multi-body dynamics, and why wouldn't you just use multi-body dynamics on doing an analysis? Well, multi-body dynamics is a really excellent tool. It's a great tool for understanding complex kinematic and dynamic interactions between components, and it's uniquely well suited for doing those types of things. But where multi-body dynamics runs into problems is when they've got to interact with the real world. So when you've got a truck driving over dirt, or you've got a front-end loader digging into gravel, the loads coming from the environment are nearly impossible to model correctly in multi-body dynamics. And what I like to say, and I know it's a little bit of a smart aleck saying, but with multi-body dynamics, when you're doing those types of operations, you're still making a guess. It's just a better guess, okay? And with TrueLoad, we can instrument up like the buckets or the axles to turn those components into load transducers, and we can then take those loads then and feed them into the multi-body dynamic simulation so that they can do the other parts. The multi-body dynamics can do the other part of the analysis that they do uniquely well. So we've got several applications where we partner TrueLoad with multi-body dynamic simulations so that they can work together and not work against each other. So it's a both and situation, and it's not an either or. And then there's one other question here. Somebody's asking about ANSYS. Does TrueLoad work with ANSYS? And yes, we can work with any FEA processor. We've got a very nice Workbench plugin that works very well. So ANSYS is a big part of our portfolio these days. So if you're using Abacus, ANSYS, Nastran, we'll be able to work with you. Okay. Okay, Ali, I think that's all the questions. I'll just turn it back over to you. Okay. Thank you very much, and thank you for taking the time today.
Yes, thank you very much, Tim. And as always, please feel free to send your questions to us. We'll be also following up with you. And I hope that this is very informative. And thanks for your participation. We will also send the recording of this webinar and a copy of this presentation to you. So thank you very much, and we'll be in touch shortly. Have a good day.
Great. Thank you, everyone. Bye-bye.